Oh, welcome back, Scouts, for Activity 23, all about science. Hemp Hill, Camino Real, Blanco Vista Elementary, and all others are welcome.
For more fun activities at home, visit our YouTube channel, Sacred Springs Scout Reach. Please join me in the Scout Oath. On my honor, I will do my best to do my duty to God and my country and to obey the Scout law, to help other people at all times, to keep myself physically strong, mentally awake, and morally straight. Please join me in the Scout law. A Scout is trustworthy, loyal, helpful, friendly, courteous, kind, obedient, cheerful, thrifty, brave, clean, and reverent. A Scout is reverent. A Scout is reverent toward God. He is faithful in his religious duties. He respects the beliefs of others. A Scout is reverent.
Show the Cub Scout sign. Tell what it means. Make the sign with your right hand. Hold your arm straight up. The two raised fingers stand for the Scout Oath and the Scout Law. The fingers look like the sharp ears of the wolf, ready to listen to a Kela. Remember that a Kela means good leader to a Cub Scout. Your mother or father or guardian is a Kela. So is your Cub Master or your den leader. At school, your teacher is a Kela.
Say the Cub Scout motto. Tell what it means. The Cub Scout motto is do your best. A motto is a guiding principle and a rule for living. Do your best means trying your hardest, not just a little bit. Do your best all the time. Do your best in school and at home. Do your best when you play a game and help your team. Do your best as you work on your rank adventures.
Bear Handbook Requirement 1 through 6. Super Science. Answering scientific questions. Scientists try to create a fair test when they want to answer a question. The steps below can help you answer questions like a scientist. 1. Ask a question. What do you want to discover? 2. Do research. What have other scientists already learned? 3. Make a good guess at the answer. This guess is called a hypothesis. 4. Test your hypothesis with an experiment. This is the fun part. 5. Decide whether your hypothesis was supported by the information you collected. 6. Share what you discovered.
Well, hi there. My name is Richard. This is my friend Jim, and we're here at Adventure Base Camp at Camp Champlin to bring you super science for Cub Scouts.
Have you ever wondered why the sky is blue, or how gravity works, or what makes a rainbow? Scientists wonder questions like that all the time, and they figure out the answers through experimentation.
Gravity check! It works. Now, the great thing about a lot of these experiments today are not only are they fun to do, but they use things that are gooey, oozy, splishy, and splashy, which are just the kind of things that Cub Scouts enjoy doing.
In this adventure, you'll get to do some science projects that are a little bit messy and really amazing.
So, put on your lab coats and get ready to do some super science. Scientists try to create a fair test when they want to answer a question. The following steps can help you answer questions like a scientist.
Step 1, ask a question.
What do you want to discover?
Step 2, do research.
What have other scientists already learned?
Step 3, make a good guess at the answer.
Okay, this guess is called a hypothesis.
Step 4, test your hypothesis with an experiment.
And that is the fun part.
Step 5, decide whether your hypothesis was supported by the information you collected.
Yeah.
Step 6, share what you discovered.
Always share what you discover.
Our first experiment is all about static electricity. You may have walked across a carpeted floor in your socks to pet your dog and gotten a shock. Maybe you've taken off your winter hat and found that your hair was standing straight up in the air. These things happen because of static electricity.
To understand static electricity, you have to understand atoms. I love the atom. He's that guy from Legends of Tomorrow, right?
Yes, but wrong atom.
Wrong atom? Not the superhero?
No, different kinds of atoms.
Oh! You know what? Everything around us is made up of very small things called atoms. Those atoms are made up of even smaller things, including protons and electrons. Protons have a positive charge and electrons have a negative charge. Each atom usually has the same number of protons and electrons, but if two atoms bump into each other, hey, Jim, did you hear about the two atoms that walked into a bar?
No.
Well, you would think one of them would have seen it. Anyway, if they happen to bump into each other, electrons from one atom can get rubbed off onto the other atom. As you walk across a carpeted floor, especially if you happen to drag your feet, extra electrons build up on your body. When you touch your dog, those electrons jump onto the dog, causing a little spark of static electricity. Why does your hair stand up when you pull off your winter hat? That happens because all your individual hairs now have a positive charge and are repelling each other. This is kind of like trying to hold the positive sides of two magnets together. For this first experiment, we're going to blow up a balloon, and then we're going to rub it against different objects to see how each object reacts to the balloon and the static electricity. So, my friend Jim is blowing the balloon up. He's using a helium tank. Hey, if you've got the lung power, you might as well use your own lungs to do it, but we're using a helium tank today. And as soon as he is ready with this balloon,
Even longer than I expected.
this just takes some time sometimes, when you don't practice the experiment first and then you just stand here talking. Ah! Look at Jim, he's so good. All right, so Jim.
All right, we're gonna rub it against this full fleece blanket. One, your hair or my hair?
Oh, you can use my hair. It's thin and see what happens. So see what happens with my hair.
Up, just there.
Oh, rub it against my hair.
Yay!
Look at that. See that? See what happens? There we go. All right. Okay, yeah, it's a look. Okay. Thank you very much. Wow. Makeup, hair. Okay, now hold it up to the blanket and see what happens. Oh, look at that. It stays and attaches itself. Now let's see. We're going to try other objects. Now take it off the blanket. There we go. All right, let's see. What happened to how does Arizona can? Oh, helium's making it float away.
Sorry, full one.
A full Arizona can. Let's see what happens here. That same thing. It's still floating away. Quick, oh, Jim!
No, it's just gonna keep being up there. What do you think was gonna happen?
Okay.
Come on.
We're gonna bring this. This is gonna happen.
Hey, we did it.
Look, we got it. So, now let's see what happens. Now that my hair's standing up, if I try to attach it to a glass cylinder, nothing. Okay, we're not gonna let. How about a feather? Nope. Look! Sticks to the Boy Scout uniform. Like I say, if your parents will let you, you can try to use this balloon, your balloon, to try to see how it reacts to different objects around the house.
Our next experiment is all about sinking versus floating. Whether an object sinks or floats in a liquid depends on two things: density and buoyancy.
Density is how close together the molecules of an object are, or how much mass a substance has in any given space. For an object to be buoyant, or float, it must have less density than what it is floating in, or it has to have something attached to it that helps it float.
Step 1. Fill all 3 cups half full with water. Step 2. Stir salt into the first cup and sugar into the second cup. Now, leave the third cup alone. Now think about what will happen when we add an egg to each cup. Do you have an idea? Now gently add the egg to the cup. This experiment shows how scientists use variables. A variable in an experiment is the thing that changes. And by changing just one variable at a time, we proved how sugar and salt affect how eggs float in water.
Now, the plain water is called the control because it doesn't change. And since the control is the same in each one, we can compare the results with the salt and the sugar and the plain water.
For our next experiment, we are going to be learning all about color morphing. For this experiment, we will be using a large jar or clear vase, enough water to fill the jar halfway, a measuring cup, a spoon, 2 tablespoons of cooking oil, and 3 drops each of red, blue, and yellow liquid food coloring. Step 1. Fill the jar or vase halfway with water. Step 2. In the measuring cup, mix the oil and the food coloring together. Next, pour this mixture slowly into the water and watch what happens. Now what is happening here? Since food coloring is water-based, it will separate from the oil and float through the water in amazing color morphs. If you have time, try different color combinations. To keep the color theme going, we are going to be doing a color layering experiment next. And for this experiment, we will be creating a rainbow in a cup using sugar, water, and food coloring. The materials we will be using are 15 tablespoons of sugar, 15 tablespoons of warm water, red, green, blue, and yellow liquid food coloring, 6 clear containers, and a spoon. First, put 5 cups in a row on the table. Add 1 tablespoon of sugar to the first cup, 2 tablespoons to the second cup, 3 to the third, 4 to the fourth, and 5 to the fifth. Then add 2 tablespoons of lukewarm water to each cup. Stir until most of the sugar dissolves. Add a drop or 2 of food coloring to the first 4 cups, 1 color per cup. In the 5th cup, mix 2 colors. Now take the 5th cup, the one with the most sugar, and pour half of its contents into the empty cup. Hold the spoon, bowl side up, against the inside of the 6th cup. Then slowly and gently pour half of the contents of the 4th cup into the spoon. Pouring onto the spoon keeps the 2 liquids from mixing in the cup. Do the same thing with the 3rd, 2nd, and 1st cups. What is happening here? Adding sugar to the water causes it to become denser as the sugar molecules take over the space. The more sugar you add, the denser the water becomes. That's why you can stack the colored water as long as you pour it gently.
We are so glad you decided to join us today here at Adventure Base Camp at Camp Champlin. Once again, my name is Richard. This is my friend Jim.
Remember, a scout is thrifty.
We hope you have as much fun doing the experiments at home and even more fun than we did putting them together for you.
And we'll see you next time.
Ow!
Testing static electricity. Which of these objects will stick to a balloon or comb? Write down your prediction and then write down what actually happened. So the left column is the item you're going to test. Whether it's tissue paper, aluminum foil, cardboard scrap, paper scrap, yarn or string, a pom-pom, a Chanel stem, ribbon, cloth, foam, coin, and the prediction is a yes or no. Will it stick or not? And the result is your answer. Requirement 3, conduct one other static electricity investigation and explain what you learned. For this requirement, fill a dry, empty plastic bottle with small foam beads, like the kind in a beanbag chair. Stand in front of a mirror and rub the bottle on your head. What happens to the beads? Now, touch your other hand to the bottle. Do the beads move toward your hand or away from it? Experiment with other objects to check the reaction of the foam beads.
Requirement 1. An experiment is a fair test to compare possible explanations. Draw a picture of a fair test that shows what you need to do to test a fertilizer's effects on plant growth. Imagine that you're a medical researcher who wants to test 3 new medicines to see which one helps people who have a cold feel better. If you give a sick person all 3 medicines and he got well, how would you know which medicine worked? You wouldn't. But what if you started with 3 sick people and gave each one a different medicine? Then you would know which medicine or medicines worked. When a scientist asks a question, he or she comes up with a fair test to answer that question. This is called an experiment. An experiment is designed to rule out possible explanations and, as much as possible, test only a single explanation. In an experiment, scientists look at 3 things. What they will change, called the independent variable. What they will keep the same, called the control variable or control. What difference they are looking for, called the dependent variable. In the medicine experiment, the independent variable is which medicine each person takes. The control is the fact that each person has a cold. The dependent variable is whether or not each person gets well. For this requirement, you will draw a picture of an experiment to test fertilizers. First, think about what independent variables, controls, and dependent variables your experiment will use. A scientist might start by creating a chart like the one below to help figure out what the important parts of the experiment could be. One of the biggest challenges in creating a fair test is to figure out what to keep the same, what to change, and how to find out if a meaningful result occurs. Measuring the impact of fertilizer. Your independent variable is fertilizer added versus plain soil. Your controls are same kind of plant, same amount of water, same type of soil, same amount of light, same temperature. Your dependent variable is how tall the plant grows. What would you add to the list of controls? What are some other ways to see whether the fertilizer made a difference? Measuring how tall the plant grows might not be the only dependent variable you could test for. Draw a picture of your own fair test to compare fertilizers and label your drawing with all the variables that you would want to keep track of in your experiment. You might draw this as a comic strip to show the steps in your test and the changes over time. One thing you'll learn about scientists is that they take a lot of notes. For this adventure, you might want to make a field notebook where you keep notes on experiments and other things you discover.
Requirement 2. Visit a museum, a college, a laboratory, an observatory, a zoo, an aquarium, or other facility that employs scientists. Prepare 3 questions ahead of time and talk to a scientist about his or her work. Scientists work in many different places. When you visit a scientist in one of those places, you can better understand what he or she does and the tools he or she uses every day. Just like you plan your investigation, you should plan your visit to a scientist. What would you like to learn? Write down your questions in your field notebook ahead of time. Before your visit, try to guess how the scientist might answer your question. Afterwards, see how his or her answer compared with your guesses.
Requirement 3. Complete any 4 of the following. Requirement 3A. Carry out the experiment you designed for Requirement 1 above. Report what you learned about the effect of fertilizer on the plants that you grew. An important part of designing a fair test is deciding ahead of time what you expect the result to be. For your fair test, that means making a prediction about how the fertilizer will influence the way the plant grows. Write your prediction in your field notebook and then carry out the experiment. After the experiment ends, compare your prediction with what you actually observed. Did the plant grow as tall as you predicted? Did the plant grow in ways that you were not able to predict? How can you explain this result? Draw a picture of what happened and make a note in your field notebook about what you would like to do to learn more. Requirement 3B. Carry out the experiments you designed for the Requirement 1, but change the independent variable. Report what you learned about the effect of changing the variable on the plants that you grew. There are lots of different ways to carry out an investigation using the same materials and variables. Here are some other independent variables you could test in the plant experiment. Potting soil versus sand. 6 hours of light per day versus 24 hours of light per day. Colored light versus white light. Fresh water versus salty water. 100 milliliters of water per day versus 1,000 milliliters of water per day. Design another fair test and write down what you predict will happen. Remember, you use only one independent variable in your experiment. Now carry out the new experiment. What did you find out? Did the result match your prediction? If not, how was it different? Draw a picture of what happened and make a note in your field notebook about what you would like to do to learn more. The more you carry out experiments like this, the more you will learn about the subject you are studying. For example, over time you might learn that a combination of factors, safe fertilizer plus plenty of sunlight, helps plant grow better than fertilizer alone. Or you might learn that a certain fertilizer works better on flowers than on vegetables. Scientists also like to repeat the same experiments over and over. They even publish the details of their experiments so other scientists can reproduce them. Getting the same results many times proves that the results are accurate and not caused by some random event, like worms in the soil affecting plant growth.
Requirement 3C. Build a model solar system. Chart the distances between the planets so that the model is to scale. Use what you learn from this requirement to explain the value of making a model in science. Our solar system is really, really big. It takes Earth 1 year to travel around the sun. But it takes Neptune, which is way out at the edge of the solar system, 165 years. Light travels at a speed of 238,000 miles every second. But it takes light from the sun more than 7 minutes to reach Earth, which is 93 million miles away. Yes, the solar system is huge. For this requirement, your challenge is to build a model solar system that has the same scale as the actual solar system. In other words, the relative distances between the planets in your model will be the same as they are between the real planets. This chart shows each planet's approximate distance from the sun, along with scale distances in both inches and centimeters. It also shows Proxima Centauri, the nearest star to the sun. The sun is what the planets revolve around, and Mercury is 36 million miles from the sun. The scale distance of 1 million miles equals 1 inch, puts Mercury 36 inches from the sun. The scale distance of 1 million miles equals 1 centimeter, puts Mercury 36 centimeters from the sun. Venus is 67 million miles from the sun, so it would be 67 inches from your sun, or 67 centimeters from your sun. Earth is 93 million miles from the sun, so Earth would be 93 inches from the sun, or 93 centimeters from the sun. The rest of the planets from Mars to Neptune and Proxima Centauri, the nearest star to the sun, complete the chart. To get started, make a series of signs, one for the sun and one for each planet. Label the signs and add pictures if you want to. Write on the planet signs how far away from the sun each one is. Now, decide whether you will use inches or centimeters in your model. An inch is more than twice as long as a centimeter, so the scale model in inches would be larger than the scale model in centimeters. Will the sun and all the planets fit in your home if you make the model in inches? What if you made it in centimeters? Get out a ruler and test your prediction. Unless you live in an aircraft hangar, the model organized in inches won't fit in your home. The distance from the sun to Neptune is more than 230 feet. That's 2/3 of a football field. You will need to make your model solar system outside. Use a measuring tape and an open space to lay out your model solar system. A schoolyard or park would be a good spot if you have permission to build your model there. You will need a friend to help you lay out your solar system. In fact, this would be a fun project to do with your whole den or family. Every Webelos scout could pick a planet and make his own sign. In your field notebook, write down answers to these questions. What is the value of making a model for things that are so big, such as the solar system? How can models be useful in science?
For your solar system model.
Requirement 3F. Study the night sky. Sketch the appearance of the North Star Polaris and the Big Dipper, part of the Ursa major constellation, over at least 6 hours. Describe what you observed and explain the meaning of your observations. Making observations of the world around you is an important part of science. The things you observe help you form important questions and start to make predictions. Your predictions, whether or not they are correct, are important steps in helping you explain why things happen the way they do. The stars and constellations of the Northern Hemisphere can help you understand changes in the night sky. For this investigation, sketch the appearance of the North Star and the Big Dipper, which is part of the Ursa major constellation, over at least 6 hours. You will want to do this on a clear weekend night when you can stay up late with your family's permission. This would be a great activity to do on a Webelos Den campout, or with your family in the backyard. As early in the evening as possible, make a sketch of the night sky. Draw it as precisely as you can so that you can see which way the pointer stars on the side of the Big Dipper are oriented. Return in 3 hours and make another sketch. Try to be precise as before so that you can accurately record any motion that you observe. Return 3 hours later and record what you see. You might have to wake yourself up or get your parent to help. Again, make your sketch as accurate as possible. Compare your 3 sketches and think about these questions. What are some ways to explain what you observed? Which is the best explanation? That the Earth is moving or that the stars are moving? How long will it take for the Big Dipper to return to where it was when you first recorded it? How could you use what you observed to tell time? What are the advantages and disadvantages of a star clock that uses a constellation?
Welcome to Scouting at Home for Cub Scouts. My name's Koala, and tonight we're looking up at the night sky. You've probably heard of constellations before, and they've been used for thousands of years for navigation. Tonight we're going to show you how to spot a couple of the really common ones and one way that you can find direction at nighttime without a compass. The first constellation we'll look at is Orion's Belt, also known as the Three Kings. It's made of 3 bright stars, all in a row, and you can imagine a straight line could join all 3. In the southern hemisphere, Orion's Belt is visible in the northwest sky, and it's best seen during the summer months. Now let's try and spot Orion's Belt in this picture of the night sky. Pause this video if you want some extra time to look. Can you spot it? Let's point it out. Let's look at another constellation. One that you'll probably recognize is the Crux constellation, also known as the Southern Cross. It has 4 bright stars in a cross shape with a slightly smaller star in the bottom right. You might recognize it from our Australian flag, and it is very prominent in the southern sky. It's also the smallest constellation in the sky. The Southern Cross has a very close neighbour known as Centaurus, and 2 stars from that constellation in particular are the Pointer stars. These are Alpha Centauri and Beta Centauri. They point at the Southern Cross, so we can use them to help us find the Southern Cross in the sky. Alpha Centauri is the closest star system to our Sun. Let's try and find the Southern Cross and the Pointer stars in the sky. Remember, you can pause the video if you need more time. How did you go? Here is where they were. One reason the Southern Cross is important to us is that we can use it to find south at nighttime. We do this with the help of the Pointer stars. So once you've found them in the sky, draw an imaginary line long ways through the Southern Cross and have it continue out into space. Then draw a line between the Pointer stars. Halfway between the stars, draw a line coming out at a right angle and follow it along until it crosses over with the imaginary line from the Southern Cross. From the point where the imaginary lines cross over, draw a line straight down to Earth. This is south. And once you know south, you can work out all your other directions. So the next time that there's a really clear night, go out and see if you can spot any of these constellations, or even if you can find south. You might be able to use some of this for some of your badge work. We'll see you next time. Good hunting, pack.
Requirement 3I. Read a biography of a scientist. Tell your den leader or the other members of your den or your family what the scientist is famous for and why his or her work is important. Reading stories about scientists and what they have accomplished can be inspiring. It may even start you on the road to your own great scientific adventure. Here are some scientists you could learn about. Albert Einstein, the physicist. Galileo Galilei, astronomer. George Washington Carver, botanist. Benjamin Franklin, researcher in many fields. Marie Curie, physicist and chemist. Paul Sipple, weather researcher and Eagle Scout. Peter Agre, biologist and Eagle Scout. E.O. Wilson, biologist and Eagle Scout. Gunyan S. Bluford, Jr., astronaut and Eagle Scout. Luis W. Alvarez, physicist. Lee Berger, archaeologist and Eagle Scout. Michael Maniak, expedition medicine pioneer and Eagle Scout. Who will be the scientists of tomorrow? One day you could become an NESA World Explorer. The National Eagle Scout Association started the program to reward Eagle Scouts who aspire to be explorers and field scientists. The Scouts who are chosen head off to the learning experience of a lifetime. Here are some recent Eagle Scout explorers. Alex Overman, Eagle Scout Argonaut. C.B. Wren, Eagle Scout Argonaut. Tristan Bullard, Eagle Scout Astronomer. Alex Houston, Antarctic Sustainability Eagle Scout.
Join us next time for Activity 24, Sounds and Musical Instruments. If you are interested in joining a pack near you, visit beascout.scouting.org.